Okay, so today we're going to do a pretty interesting technique of integration. It's called partial fraction decomposition. If you go on and take a course in differential equations later, I mean, this will be useful to us right now. But if you go on and take a course in differential equations later, then you might see something called the Laplace transform, in which case you're going to need partial fraction decomposition. But even if you don't take differential equations, this is still going to be useful to you pretty soon. Okay, so we start off with a question. Okay, suppose you have two polynomials. You have two polynomials, p of x being a0 plus a1x plus a2x squared plus am x to the m. Okay, so you have one polynomial of degree m, right? These a's are constants, you know, like 1 plus 1x, 1 plus 2x plus 3x squared, or something like that. So these the a sub I are constants, right? The a sub I are constants, right? And you have another polynomial, q of x, that's b naught plus b1 x to the 1 plus b2, b sub 2 x squared plus bn x to the n. Okay. And again, the bi are your coefficients. Okay, so you have two polynomials. One, they're not necessarily of the same degree. One is degree m, the other is degree n. Okay. And suppose say you know that p of x and q of x are the same in an interval, in a little interval, negative delta, delta. Okay? So you've got these two polynomials. But in a little interval around 0, right? In this little interval centered around 0, they are the same. Okay, so they agree with you. Like here's q and here's p. They've got this. They're the same. Okay, so they agree in a what's called a neighborhood of 0. So in this interval between negative delta and delta, they are the same. Okay. What can you say about them? What can you say about these two polynomials? What do you think? Can anyone guess what we're going to say about these two polynomials? Kara?
Do they have the same integral?
Do they have the same integral? Well, that'll be true. Maybe you mean over this interval here? Sure, that's true because they're the same function here. Okay, so they agree in this tiny interval. I don't know, maybe between negative a billionth, negative a millionth, and positive a millionth. So there's a tiny interval that they agree on. Okay, now let me ask you a question. Is a naught the same thing as b naught? Is the constant the same? Must the constant be the same? Hannah?
Are the same?
Are the same? So okay, let's take a vote. Who votes for they're the same? No, talk to somebody nearby and say, what do you think?
think it depends how big and if it could be the same version.
Okay, now we're going to have a vote. Who thinks that the constants a naught and b naught must be the same? Okay, who thinks that they not the same? And then there's some people who don't want to commit. That's okay. Okay. The answer is that they are the same. Now, why is that? Those of you who, yes, go ahead, Hannah.
When x is 0, they should have same y-intercept.
Yeah.
Which means that
Yeah.
all of them goes
Right.
0.
Just look, right, exactly. Look at the picture, right? Where is a naught on this picture? Well, a naught is right here, right? Where's b naught? Well, b naught's right there also, right? So a naught and b naught are the same, right? So a naught and b naught, right? So p of 0 is a naught, q of 0 is b naught, but p of 0 and q of 0 are the same, right? Because in this neighborhood of 0, the functions are the same, right? So in this whole neighborhood of 0, the functions are the same. At 0, the functions are the same, right? So p times 0 and q times 0 are the same thing. That tells you that a naught and b naught are the same. Okay. Okay, so you know that those are the same. What about a1 and a1 and b1? Are those the same? I'll give 2 points to the person who figures out there's one thing that you need to consider. And if you make that shift, I'll give you 3 points, say, on the exam. You should say, consider blah, blah, blah. Say, well, if you think about the something.
If it's a positive or negative number.
Say it again?
Like if it's a positive or negative number.
What's a positive?
A or B.
No. I mean, are you trying to fill in what the whatever is?
Yeah. I mean, like.
Okay, so no.
Well, we only know that p of x equals q of x along the interval. So the constants could, they'll change because like the graph will start changing for each value, right?
So you're saying that these are not going to be the same?
Yeah.
Okay. Everybody talk to each other for just 20 seconds or so.
I guess it looks
Hey, Julie, you and Mr. Al can talk to each other. You're right next to me. Okay. Proceed.
So I think that A1 and B1 are going to be the same only if those two functions are of the same degree, meaning M and N are the same.
Okay. Why do you say that? So they're both polynomials. Yeah. Why does this have to do with? Why would this be the same only if these guys? So like, how does that force these guys have to be the same degree? Why do you think that?
So I'm thinking about that because like, if their integral has to be the same, meaning their area has to be the same,
Okay, yeah.
and they have the same.
The areas definitely are the same.
Not the same.
Yeah. I mean, from here to here, they're the same function,
Yeah.
right? P of x and q of x are equal in this interval here. Mr. L.
Well, she says that since they're equal, take the derivative, they still should still be equal. Consequently, we are in a situation like we were before, where now the new a sub 0 and b sub 0 are actually a1 and b1.
Julia gets the 3 points.
Absolutely.
Julia gets the 3 points. Consider the derivative. Consider the derivative. You say, well, look, p prime x is going to be a1 plus 2a2x plus 3a3x squared plus m a sub n x 1, right? Q prime x is going to be b1 plus 2b2x plus n b sub n x 1. Okay. Now, in this interval, the derivatives are going to be the same because the functions are the same, right? Right. So we know that p prime and q prime are the same, right? Whatever they are, p prime and q prime are going to be, since the functions are equal here, the derivatives are going to be equal here, right? So we know that p prime of 0 and q prime of 0 are the same, but p prime of 0 is a1 and q prime of 0 is b1. Okay, so you see that a1 and b1 have to be the same, right? And so on and so forth, right? You differentiate again, you see that 2a2 equals 2b2. You differentiate again, you see that 6a3 equals 6b3, and so on and so forth, right? So all the coefficients have to be the same, which will force the degrees to be the same, because at some point you're going to get a 0 coefficient, and that'll make a 0 coefficient, right? At the point after which you get 0 coefficients, all the coefficients are still going to agree, right? And so the degrees are going to be the same. And so the coefficients are going to be the same. So all the coefficients are identical. Okay, and so the polynomials are the same. Polynomials are identical. Okay. So what this says is that if you have polynomials and they agree on a tiny, tiny, tiny interval, they must agree on all for all time, right? If they agree on a tiny interval of time, they will agree for all time. Okay. Right? In other words, the behavior of a polynomial is very constricting, right? If I make a tiny mark somewhere, and I say I've got a polynomial that looks like that agrees with this, well then, right, if I have one polynomial that does this, I have another polynomial that agrees with it on the tiniest of intervals. It's got to be exactly that same polynomial. Okay. Okay. This is what's called the Identity Theorem. Identity Theorem. Two polynomials that agree on an interval AB must be identical. Mr. Allen.
This is really weird, but I thought of something. Take e to the x, which is always the same derivative.
Yes.
Couldn't you use that to make, since we use the derivative here, to make a polynomial that is equal to e to the x? In other words, let's say...
Mr. Allen, I would give you 3 points for that if you actually were getting a grade. But that's great. That's great. So you yes.
In other words, yeah.
Yes. So the answer is yes.
Oh, okay. Very good. I just...
Now, do we have time for this? This is great. So, what would be the polynomial for e to the x?
Well, you're going to get a 1 at the beginning.
Yeah. So you'd say, well, you get 1, and then
it's got to be 1, so it's x.
the x.
Then x squared over 2.
x squared over 2, and then
Let's see.
x cubed over 3 times 2, right? X to the 4th over 4 factorial,
Yeah.
and it would keep on going forever,
Yeah, I
right?
guess.
It would go on forever. Now this is what we're going to get to in the second half of the course. This is what's called a Taylor polynomial. Taylor polynomial. You see, you get this infinite sum. The second half of the course deals with infinite sums. Well, we'll be talking about how do you take a function and represent it as an infinite polynomial.
So now you can calculate
Yes.
football.
Yes. Yes. Okay. Okay. So we're going to need that identity theorem to do this thing called the partial fraction decomposition. So partial fraction decomposition. Okay. Now, partial fraction decomposition will be used to integrate so-called rational functions. Rational functions. Does anyone know what a rational function is? You might have encountered this term at some point. Rational function. You all know what polynomials are, right? A rational function is one that can be expressed as a quotient of polynomials. Okay, so it'll be one polynomial over another another polynomial. Okay, so for example, say like 1 plus x squared over 1 plus 2x plus x cubed plus x to the 5th. Right, you have one polynomial divided by another polynomial. It's an analog of a rational number, right? Rational number is a ratio of 2 integers. Rational function is a ratio of 2 polynomials. Okay, and we, just like you have improper fractions, you can have improper rational functions. So if the degree of p is less than the degree of q, then we call p over q proper. We call it proper. So this one is proper. This example is proper because we've got x squared over x degree 2 over degree 5. Right? Otherwise, it's called improper. Otherwise, it's called improper, right? If the degree is the same or if the degree is greater on top. Okay. Now, just like with if you have an improper fraction, right, you can express it as, the sum of an integer plus a proper fraction, right? We can do the same thing with improper rational functions. So you can express improper rational functions as polynomial plus proper. Okay. So for example, if I have x to the fifth plus 2 over x squared minus 1, then I can do a long division on it. Just like you divide numbers, you can do a long division on polynomials. Okay, you say, okay, let's figure out what this is. Well, x to the fifth plus 2 over x squared minus 1, we're going to see is, well, you just do your long division. You say, okay, I've got an x squared, so I'm going to multiply it by x cubed. Right? I get x to the fifth minus x cubed. Right? I subtract, I get negative x cubed plus 3. Right? I multiply this guy by negative x, right, to get the negative x cubed. I get negative x cubed plus x, and then I get a 2 minus x. Right? That's my remainder, right? And so I get this plus 2 minus x over x squared minus 1. Okay, so that would be so you can, the point is that you can do long division on polynomials. Okay. Okay, so what's the point of this remark? If somebody says, can you, I'd like to know how to integrate all rational functions. You say, well, we don't have to worry about the improper ones, right? Because any improper one will be expressible as a polynomial plus a proper one, right? And we know how to integrate polynomials. So the only thing we have to worry about is the integration of improper rational functions, right? The integration of proper rational functions, right? Any improper one, we can break it into a polynomial plus a proper one. Any improper one, we can express as a sum of polynomial plus a proper one. Okay. So we just have to deal with proper ones. Okay, so that's our topic. Integration of proper rational functions. Okay, and our technique is partial fraction decomposition. Okay, so so here's the theorem, and I'm afraid this is one that we're not going to explain. We're just going to tell it to you. That every proper rational function can be expressed as a sum, can be expressed uniquely as a sum of what are called partial fractions. That is, functions of the form. Let me move this up because there are people in the back. I can't see it. Partial fractions, functions of the form some constant over x minus some constant to a natural number, or something linear over x squared plus beta x plus gamma to some constant right, where beta squared minus 4 for gamma is less than 0. Every proper rational function can be expressed as sums of things that look like this. Things that look like this. Let me write down a couple of examples to make this clear what we're talking about. So 2x squared plus 3 over x times x minus 1 squared turns out to be 3 over x plus negative 1 over x minus 1 plus 5 over x minus 1 squared. Okay. So proper rational function, here you've got your proper rational function. Turns out that you can express it in terms of these partial fractions, right? These three guys are all this form, right? Some constant over some power of x minus a constant, right? Some power, the first power of x minus 0, the first power of x minus 1, the second power of x minus 1. I've got constants on the top. I'll put up a few examples. X squared plus 5x plus 2 over x plus 1, x squared plus 1, turns out to be the same as 1 over x plus 1 plus 2x plus 3 over x squared plus 1. So again, you've got this proper rational function. It turns out you can express it as a sum of partial fractions. Here's one of these guys. This is from the first form, right? The guys with the linear terms on the bottom. This one is one of the second form, the guys with the quadratic terms on the bottom. Okay, and notice this thing here, b squared minus 4 gamma being less than 0. That tells you, what does that tell you about the quadratic you've got here? If beta squared minus 4 gamma is less than 0, you know something about the roots here. You should have seen this at some point in the quadratic formula, I'm saying, right? This tells you that the roots are complex, right? That you can't break this up any further. You can't, this is an irreducible quadratic. The quadratic is irreducible over the real numbers. Right? Right? X squared plus 1 has no real roots. X squared plus 1 has no real roots. It has imaginary roots, like I, negative I, but no real roots. So two kinds of things can show up. These guys with powers of linear terms on the bottom. These guys with powers of irreducible quadratics on the bottom. And that's what showed up here. One more example. So 3x to the 4th plus x cubed plus 20x squared plus 3x plus 31. Why did I choose this so long? X squared plus 4 squared. Turns out to have the following partial fraction decomposition. 2 over x plus 1 plus x over x squared plus 4 plus negative 1 over x squared plus 4 quantity squared. again, this is just an example of something that has, somebody of the first form and these two guys of the second form, right? With the powers of quadratics on the bottom. Okay. Okay. And so these expressions are called the partial fraction decompositions of the function, right? This is the function, this is its partial fraction decomposition, right? We've decomposed it into a sum of partial fractions, right? So this thing here is called the partial fraction decomposition of that thing on the left. Right? This is the partial fraction decomposition of this. This is the partial fraction decomposition of this. Okay. And you see that these things, that the partial fractions are easier to integrate than this, right? They look pretty familiar, right? In fact, you might recognize what we have to do with it from last class. So your question at this point should be, how do you get the partial fraction decomposition, right? How do you get the partial fraction decomposition? So here's the method. So given p of x over q of x, first thing you do is you factor q of x into irreducible terms. Okay, now that will be either linear, those terms will be linear terms and maybe quadratic terms. Okay. Right. Any polynomial can be factored over the reals, can be factored down into linear and quadratic terms. Okay. Although I should say that in general this is hard to do. Right? If somebody just gives you a polynomial, right, in the homeworks, it'll be already broken down for you. Right? They'll give it like this. But if they had given it in this form, say, and said factor it into linear and quadratic terms, that wouldn't be so easy. Right? They are a formula, but only up to a certain point. Okay. Okay. So once you've got the factorization, so if the factorization contains something of the form q minus alpha to the k, then the decomposition can contain partial fractions of the form a1 over x minus alpha, a2 over x minus alpha squared, a3 over dot dot dot, a sub k over x minus alpha to the k. Okay. Okay, so look at this last example that we left here, right? When you factored the denominator into irreducible terms, we have this one linear term to the first power, right? That tells us that we can have some constant over that linear term to the first power, and that's it. Right? If this were a square, then we might also have some constant over the linear power squared. Okay, but then we'd stop there. Okay, so this this, this term and its degree tell you that you can have these terms up to a certain degree. Okay. Similarly, if the factorization contains some x squared plus beta x plus gamma to the k, you can have things that look like some linear term over the bottom to the first power, some linear term over the bottom to the second power, dot dot dot, linear term over the bottom to the k power. Okay, so here, hold on, I'll wait. Okay, so again, in the example, we've got this quadratic to the second power. So we can have terms that look like something linear over the bottom to the first power, something linear over the bottom to the second power, and that's it. There's no way we're going to get things like some term over this thing to the third power. That won't occur. Okay, so I'm afraid, like I said, that we're not going to prove this, but it would be too long. But this is, I'm afraid, just take this as a fact. So there's two parts to it, two parts to this method. First is figure out what the partial fraction decomposition might have in it, right? So you say, okay, I've done this. I figure out that it could have things that look like this and things that look like this, and then you need to use some method, and we'll show you a few to determine the coefficients. To determine the exact coefficients, right? Because at this point you only know, you know that it has terms that look like this, but you don't know what the constants are, right? You don't know what the AI, the BI, and the CI are, right? Okay, but we're not going to do this last part today. Right now, we'll just do some practice of parts 2 and 3, just to make sure that you got the method down. Okay, so here's my first example. If I have 1 over x squared minus 4, then what kind of terms can I have in its partial fraction decomposition? Take 1 minute and run through this first 3 steps. Okay, turn to somebody nearby and tell them what you got. with me? Somebody want to tell us how to do it? Ms. Pisky?
So I separated the x squared minus 4 into the quantity x squared minus 2 times the quantity x minus 2 times x plus 2.
Right.
And then I used step 2
Exactly.
to say that it would take the form a1 over x minus 2, and then the second portion would take the form a2 over x plus 2.
Okay. Right, you've got these linear terms, right? They're each to the first power. So you're going to have things over the linear term to the first power. Nothing more than that. Okay. Okay. Right. Okay. X squared plus 5x plus 2 over x plus 1, x squared plus 1. Okay. And like I said before, we don't, at this point we don't know what the constants are, but we'll figure them out later. That's step 4. We'll do that next time. Okay, turn to somebody nearby and tell them what you got. Okay. Anybody? Somebody want to tell me about it? Joanna, how about you? You're confused. Okay, that's all right. So the way you do it, you say, okay, look, I've got this linear term, I've got this quadratic term, right? The linear terms are going to give me things that look like this. The quadratic terms will give me things that look like this. Okay. So you say, okay, I've got this linear term to the first power. So it's going to give me some constant over that linear term to the first power. Okay. And then the second one, well, I've got this quadratic. It's an irreducible quadratic to the first power. So I'm going to get something like this over the quadratic to the first power. Okay. And that's the end. Okay. That's basically the whole method right there. I mean, parts 1, 2, and 3. The only variation is if you have some powers on it. Suppose I have a cubed here and a fourth. No, let's not do that. A squared here. Okay. Suppose I have a cubed here and a squared here. Well then, I'd say okay. Since these guys go up to the third power, I could have some other constant over this guy to the second power plus some other constant over this guy to the third power. Okay, right. So those are the partial fractions that contributed by this thing. Okay, and then you got this thing to the second power. So you say, okay, well I could have something linear over the quadratic to the first power plus another linear function over this thing to the second power, but that's it. Okay, so That's it. That's it. Right? You just look at this thing, and then you put up the appropriate terms. Okay, that's it for today. That's it for today.